Look at any screen today. Algorithms are optimizing logistics networks in real time, drafting legal contracts, and debugging code faster than human teams can type. This diagram maps the dependencies. AI now acts as the load-bearing infrastructure for medical systems, financial markets, and military operations. This chart projects the probability of reaching artificial general intelligence, systems that can equal or exceed human cognition across the board. The curve doesn't plateau. Forecasters now place an 80. If artificial intelligence is the new resource we breathe, we have to ask, what is the physical organ actually manufacturing it? Answering that requires stripping away the digital interface entirely. We need to look at the actual architecture holding this ecosystem together. This schematic breaks down the stack. Those scattered geometric shapes represent the application layer, competing startups, medical tools, and financial software. Below that sits the intangible driver, the massive language models and neural networks. They power the apps above, but are dependent on raw processing power. And this dense foundation is the physical bottleneck. Here, the theoretical potential of software slams into the hard limitations of material science and advanced manufacturing. You don't map the future by guessing which floating shape at the top survives. You look at the singular bedrock at the bottom, because its physical limits dictate the survival of everything above it. In our current global supply chain, that foundational block is essentially one entity, Taiwan Semiconductor Manufacturing Company, or TSMC. Look at this structural comparison framing TSMC as the literal lungs of a developing civilization. The system inhales massive amounts of raw capital and electrical energy, passing it through the silicon architecture to exhale the computing power shown on the right. Every breakthrough in machine learning requires more of that output. The pace of our scientific and cultural advancement is now directly tethered to how fast those fabrication plants can push electrons through nanometer-scale transistors. If that manufacturing process hits a physical wall, the march toward general intelligence stops. The software cannot outpace the silicon. Recognizing this hard physical limit means we have to discard the old ways we measure both progress and risk in the tech sector. This highlights the shift. Traditional logic relies on dispersion to protect against market volatility. The singularity model follows a different geometry. Because the digital stack depends on a single physical foundation, diversification increases risk, demanding focus on the bottleneck. Under this model, the definition of risk changes entirely. The danger isn't that an asset's price might fluctuate. The actual threat is misallocating resources and missing the window of a major evolutionary leap. This diagram maps the structural boundaries of that risk. The physical manufacturing base becomes an absolute defense zone. It is the single required anchor, surrounded by the chaotic variables of geopolitics, natural disasters, and unknown systemic shocks. These fabrication plants function as high-pressure crucibles, manipulating matter at the atomic level to forge the cognitive engines of the next century. So if we want to understand where human capability is actually heading, we have to stop staring at the code. The future isn't being written in software, it's being built, atom by atom, in the bedrock.